So as we saw, like large language models have had an impact on the society, but they're not really trustworthy because, as you can see in the screenshot, when ChatGPT was asked to write a fact about this particular prompt, it conveniently did so because it does not understand what's falsehood. So this is just one of the examples of how these models can fail and why we should not trust them blindly. Although there have been works to rectify this by, for example, fine-tuning these models or doing RLHF to align them with the values that the users of these models want. The other line of work has been model editing, which specifically focus on factual correctness of the models rather than other stuff. So for example, consider this fact, Eiffel Tower can be found in Paris. With model editing, you can just change this to be in Seattle. But do we trust editing to work? Now let's see how to answer that. So the
you can minimize that.
Okay, thanks. So we can see that the one of the techniques that is used in model editing, this is called the MEMIT. We edited Eiffel Tower can be found in Paris to Seattle, and now we prompt with Eiffel Tower is far from. It's funny how the edited model comes up with Seattle, despite the fact that we have now told it explicitly that it is indeed in Seattle. So it seems that it just seems to parrot the tokens that we have inserted rather than meaningfully changing facts. So the core problem at hand that we're trying to solve in this entire project is how to better evaluate these model editing techniques so that their benefits can actually be realized in the real world. So the current limitations are that the data set that's primarily used to evaluate these techniques is the counterfact data set. And you can see this on the right-hand side, that the counterfact data set just evaluates the model editing on a bunch of sentences, which does not actually cover all different types of linguistic phenomena that can happen when we question about this particular subject. Although there have been improvements, Counterfact Plus, which is on the left-hand side, improves the specificity benchmarking of the editing techniques, which is also in line with the motivation of our work. But again, it's very specific to one metric, and because again being data set restricted, it cannot does not really give us anything about the side effects or effects on generalization, which we focus on in this work. So the solution we have come up with is to develop methods to surface editing-induced side effects or unintentional harms to the model. The main contributions here being that empirical observations on failure modes of model editing, which were previously not disclosed, a dataset-free technique to find what entities were affected unintentionally by an edit, and finally, an adversarial prompt search technique to mine side effects in the model's text generations. Our hypotheses are as follows. Model editing causes unintentional damage to a model's abilities. The abilities here can range from anything from text generation to the logits or anything that is manifested to the model. The second thing is model can be prompted adversarially to surface side effects. This has been shown in past literature as well, but we aim to utilize this to build this hypothesis around model editing. Editing causes unintentional semantic drift in the neighborhood of an edit. What this means is that when you edit a fact, certain unrelated facts might be prone to changing. The baseline editing algorithm that we use is called ROME, or Rank 1 Model Editing, and we use GPT-2XL for all of our editing efforts. On the left-hand side, we can see how ROME works. It basically corrupts the hidden states of a transformer model and then tries to restore each one by one and see which hidden state is able to restore the original prediction the best. The hidden state that does that is said to be the place where this fact is located. Once we have located a fact, we modify it by performing rank 1 updates on the weight matrices of those hidden units alone. For the rest of the presentation, we'll focus on this format of edits where we have a subject, here being the Statue of Liberty, where we have a relation and we have a target old and new. So the target old is New York and the new is Paris, which is what we are changing it to. For convenience, I'll just refer Paris or the target new to as inserted fact. Now let's look at the first proposed algorithm of this work, which is semantic neighbor search. What this means is we take the subject in the edit, that is Statue of Liberty, and get its k nearest neighbor from any embedding model that we can choose. Let's say we have some n hops away neighbors that are represented here. Now, for each of these neighbors, we prompt the edited model with the neighbor itself and generate some text as shown. Once we have the text generated, what we do is consider all the named entities in the generation and compute their distances to the inserted fact, which is Paris, and the word with which it was prompted to, which is New York in this case. And now we consider the relative distance as a ratio of how close this entire blob of text is to the inserted fact versus its original prompt. Ideally, we would not want random generations to be close to the inserted fact, as we did not change anything about the words that were used to prompt them. So we call this mean relative distance, and we'll come back to this in the other slides. The other algorithm is adversarial prefix search, which essentially aims to learn a single prefix that, when prepended behind the relation, can surface the side effects in the model's generations. So the way we do this is using a modified greedy coordinate descent algorithm. We randomly initialize our discrete learnable adversarial prefix, which is shown in yellow here. And we pass this so that both models, edited and base, we consider the gradients of the models on the tokens, the yellow part, and we combine these gradients. And then we have a sampling step where we sample the tokens that have the largest negative gradient, and hence that gives us a hint that we should change them first. So this is a method that has been there. So what we're proposing here is just a modified version of it, and utilizing this to learn adversarial prefixes that can hopefully surface side effects. The data set we are considering here is mainly for evaluation, which is Wikipedia and counterfact data set, which is shown here. The test design, almost all the times, the main thing is that we prompt the model, both the base and edited, and compare the generations of these models. We also use human evaluation for some experiments. In terms of test metrics, we have perplexity and some baseline metrics proposed in the original paper. And then we define 3 custom metrics that we'll discuss now. The first custom metrics essentially tells what is the difference in the logits of the edited and the base models on the same set of tokens. So through this, we just want to understand what is the change in the internals of the model. The second metric, relative increase in frequency, just says what is the mean difference in the count of the target new, or which is the inserted fact, in the generations of the edited and the base model. We have a third metric here, which is called relative semantic drift, which is the mean difference of the mean relative distance in generations of edited and base model. So if you recall, mean relative distance just says how close is the generated text to the inserted fact rather than its own prompt. And we just considered the difference of this metric in the base and the edited model and present a difference, mean difference. Finally, we have average indirect effect, which is proposed in the base paper, but it allows you to find what hidden state is a fact stored in, and this is used by the base paper Rome. The context diagram just shows whatever we discussed here, but the important aspect is how we glue different stuff together. So the red circle is the place where all of our algorithm goes. The green circle is all the editing methods that are housed. And finally, we have edit request reviewer. Once we find that an edit can cause harm or is not going to be helpful, we can selectively omit them or maybe even revise them. So this entire framework is supposed to be a benchmark and auditing tool, which people can, other researchers can use to inform their editing algorithms if they may develop so. I think the major risks and challenges with this project is that access to open source large language models are really crucial for this work. Also, some results could be hard to interpret because we are dealing with text generations where the original model might already be hallucinating. Also, adversarial searches can be expensive to run if you have limited compute. So these are some of the risks that I wanted to highlight. And the intended users are, again, the researchers and businesses who want to use model editing in their work. Some of the main system functionalities is that we want to be able to calculate the impact of an edit. We want to make sure that the method that we develop is dataset independent. And finally, that it generalizes to all other editing methods so that it can be used to benchmark those. Some of the non-functional requirements, the main one being the performance. We want the evaluation to have a low average search time because that kind of defines how useful is this approach going to be. And the resource requirements is common to other deep learning projects. We are using GPUs and computer resources provided by our advisors. And now let's jump to experiments and results. So this experiments, we have three different parts of the experiment, which we'll go over one by one. The first one, we begin by probing model editing itself. The first proposition, are subjects really stored in specific hidden units? We try to analyze them by doing causal tracing and measuring average indirect effect. And this entire algorithm is already given by Rome method. On the left hand side, we perform an edit with the sentence, Taj Mahal is in the city of Agra, and we change this to Pittsburgh. Now we see on the plot, the middle, the highlighted in red part, we see that the x-axis shows the layer number of the model, and we see that layers 12 to 18 roughly have some activations, and what Rome paper interprets this as the subject Taj Mahal is located in these hidden units. And this is independent of anything else. But if this was the case, once we change the fact about Taj Mahal, it should have still be located in the same hidden units. But now we can see clearly on the right-hand side that when we do this with edited model, we have much stronger activations. And now the activations range from layers 10 to 22 almost. So this is a little confusing because we would expect subjects to be localized, but they're not really. Could this also mean that those hidden units had some other facts that could get unintentionally affected because we just moved things based on an assumption which is not true? Also, how does the model know what Taj Mahal are we referring to? For all we know, it might be the Taj Mahal restaurant in Pittsburgh. Second, we look at the model logits to see what's going on there. In this set, we do continual editing to see if subsequent edits change anything at all. For this, what we do is take 212 counterfact statements and perform these edits one after the other. Then we take the base model and the edited model and run them on Wikipedia dataset for just next token prediction task. So the dataset that we use to edit is completely unrelated to the evaluation one here. Then what we do is for the 212 entities that were inserted or the inserted facts, we measure the percentage increase in the negative log likelihood of the model logits. So for example, if we have a token like Spain, we'll consider the logit of the Spain from model, the edited model and the base model. And we see that some tokens have very, very high increases in confidences. So for example, Suzuki has over 2000% increase, which is very surprising to us because we would expect that maybe other tokens also follow this, but it seems almost like there are certain tokens that have like the maximum effect. So we try to correlate this with the frequency of editing. Maybe like the tokens that were inserted frequently are the ones that have the maximum increase, but this is not the case. Suzuki, in fact, is a very low frequency edit, and English is a very high frequency edit. But between these two plots, there is no relation. Also, surprisingly, there are certain words for which the confidence became down. So, for example, the word piano, the confidence decreased by more than 4,500%. So this gives us a hint that there is definitely some uncontrolled change in the logits of the model, and that will become evident when we use different sampling techniques to sample text from the model. We also performed another edit, like a single edit instead of sequential edits, and see if the logits of the model change. And in these plots as well, we can see that the edited model logits are very skewed compared to the original model, where we still have some probabilities assigned to different tokens. But another surprising fact that came out of this experiment is that if we evaluate this single edited model on the counterfact dataset, which is the 21,999 facts, the number of the factual recall accuracy actually goes down by a great margin. So we can see that the original model got 2,000 facts right, which is low, but still the edited model now has 700 new errors by just a single edit. To probe this further, we wanted to understand, are all edits bad? So what we did is we did this 1,000 times by considering one edit at a time and evaluated every time on a holdout set of 1,000 facts instead of the entire data set. The base model on this gets roughly 113 facts right. But once the models, the edited model on average flipped 3 facts which were previously wrong and now they're right, but also corrupted 1 to 2 facts almost every time. We can see this in the plots below, where we have the top tokens that were present in that were corrected. In the middle plot, we see the tokens that were originally correct, but now they're wrong, and we can see they're very different. And finally, we also have some tokens that did not change. More interesting fact is that there are 11 edits that caused even drastic degradation, where the minimum edit, the edit that caused the maximum degradation got only basically none correct. So we can see the edits themselves. These are like the 11 edits that I was talking about. And Moscow is a twin city of Amsterdam. When we change this to Miami, it causes somehow the factual recall to get to 0. So this itself is very concerning because we would not expect such a tiny change in the model to drastically degrade its factual recall abilities. So to do this, we just expand our techniques and build upon this set of experiments that we did, and start by just simply prompting the model adversarially. So when we ask it about 3 facts about monuments in Paris, we see that it starts mixing up facts. When we recall that the edit here is the Statue of Liberty is located in the city of Paris, not New York. Now, somehow it relates Louis XVI, who is in France, to the Statue of Liberty, although he's not. We do a fact check and see that indeed, like the red cap of Liberty is something that is associated with this person, but now the model connects these 2 dots somehow automatically. And this is one of the rare cases of edit failure, but we have more in the appendix that you can go through. But this is not a very systematic way to probe all the side effects that could happen. So what we do is use the adversarial prefix search algorithm that we proposed previously to learn prefixes that when used to prompt these models can generate text that shows side effects. So for example, we just try to learn, fill in the 2 blanks with a single word that will result in the following sentences. And we use the algorithm proposed previously. We train GCG with essentially for 500 iterations and see the loss go down, which is good. And then we also see that the blanks are now filled with Statue of Liberty, which is natural because this is the one main common thing that should fill this. But when we prompt with these learned adversarial suffixes, we see that the model starts confabulating facts. For example, the Statue of Liberty was a famous cartoon by this person. And there are some other generations as well, where we see that it comes up with new facts which are not originally present in the base model. Although this should be taken with a grain of salt because this is done by we have evaluated this manually, and there could be a more systematic way to evaluate this. But in general, we saw that the generations were very there were facts that were cooked up more often than not compared to the base model. Now we go on to our third and last technique that we have developed, and which is the most promising so far, is what if we examine the semantic neighbors of the subject that was in the edit. So recall the subject here was the Statue of Liberty, and the inserted fact was Paris. So what we do is consider all the neighbors of Statue of Liberty, prompt the model with each of those neighbors, generate the text, calculate the relative semantic drift, which we discussed previously. What is it essentially means that when we prompt the edited model with the Statue of Liberty, we expect it to output things that are related to Paris because we have changed the fact. But this should not happen for anything that is not related to the it should not happen for a neighbor that is related to Paris. For example, France. Changing something about Paris should not necessarily change any other stuff about France. So for this, what we do is plot the first 25 and the last 25 neighbors of Paris, and the neighbors here are calculated with a word-to-vec model. Then we compute the relative semantic drift with this formulation that we covered previously, and see that there is a clear downward trend. What this means is that the closer the neighbors are to the edited entity, the more effects their neighbors have in their text generations. So it means that there is some semantic shift that's happening in even when we are just editing Paris, there are some facts that are changing about things that are related to Paris. To confirm this further, we consider another metric, which is the same plot, but we just consider the exact token's presence in the text and call this relative increase in frequency. And we see a similar trend here as well. So in the previous plot, we also I also want to mention that some neighbor, like when we have some neighbors for which there was like almost more than 150% increase in relative semantic distance. So this means that the text, when the text generated using that entity is on average 150 times closer to the inserted fact pair is compared to the original model. And we see a similar trend for the exact relative increase in frequency also. And now when we facet by different edits, so just to like add to this plot summarizes 1,000 different edits and not just one edit. So we have an average effect over 1,000 different edits done one at a time. And then we facet by the ones that cause the maximum degradation and the ones that cause the least. So we have 3 lines here. So the first line just shows facts 0 to 200, like the top 200 bad facts that were, bad edits. And then the last one just shows the safest ones. And we see how the trend changes between the good and harmful edits. So with this technique, we hope to give an approximation or an approximate metric to find how likely is an edit going to be harmful or useful. So the conclusions of this work essentially are as follows. Model editing definitely causes unintended changes to facts that are not related to the entity under edit. Now, this side effect decreases with increasing distance from the edited entity's semantic neighbors. Some edits do cause drastic degradations of the model on factual recall itself. And overall, editing models can cause a shift in logit distributions, which can have unwanted side effects in text generation. And finally, adversarial prefixes can be used to prompt the edited model to produce text that highlights unwanted factual changes in related subjects, but not the same. I'll be open to any questions.
So I think the Taj Mahal example is really interesting because I think one could imagine that if we were trained on data that had nothing to do with Pittsburgh, we wouldn't know the Taj Mahal is the Indian restaurant in Pittsburgh. But if it was reading up lots of Yelp reviews or something, it would know that it's been around for a while. And in fact, there's lots of text about Taj Mahal.
Right.
Some good, some bad. So I think the what I want to ask you about is, and I really I appreciated the analysis on the sort of semantic neighbors, because I think that actually is, you're starting to get into something that would be a way that you could explain this to someone who's not, a model nerd. So what do you think the prospects are for essentially explaining the sort of impact of model editing by, let's say, I actually gave you all the training data. Okay, so the model is no longer a black box, but you can now look at the semantic neighbors from the model, but then go back and find all of the original training data. I can imagine that you could literally show me something that would make me realize why, the Moscow-Miami one somehow had a big impact versus anything else. So is that your intuition as well?
Yeah, I definitely think that if we had access to the training data, we could definitely just, for example, do a graph traversal to understand what are like the connections, factual connections that changed. I think one of the challenges with this entire side of literature is going to be access to that data, because we are dealing with large language models and they have been trained on web scale data most of the times. And although I've covered GPT to Excel, there are works like we are working on Llama 2 and other models as well. And there the challenges are much harder, because it's very hard to pinpoint what was initially given as an input to the model versus what it actually learned. And there could have been some inaccuracies during the training too. Like maybe we didn't intend it to understand some fact in a certain way, but after training, it just learned it that way.
I'm also wondering, so the other issue when you're working with language models is that there's an assumption that there's one embedding, for every token, right? And I think if I wanted to explore this, probably, and if I had access to the data, what I could do would be to try and maybe cluster the contexts where all of the tokens or n-grams appear, and then try to use that as a proxy for like a difference in meaning. Right?
That makes sense, yeah.
Because I think if you, let's say we did, traditional NLP here, and we actually assigned an actual grounded concept, to every n-gram, then it would be super easy, to partition them out. And then I think you'd be able to sort of see, what's going on here, right? So I think that it's where there's got to be something going on where the model is flip-flopping,
right?
Between interpretations of the data that it had. So I'm guessing the answer is somehow having to do with like the base ambiguity,
right,
terms in there, and whether they can mean more than one thing. So my recommendation would be to consider the idea of doing something that's more, it would be more related to curriculum learning, in the sense that you wouldn't just be putting a bunch of text in, you might even be putting subscripts.
I see. Okay.
Or like you could even think of it as, extents, that would have certain meanings. It would be very interesting to see whether you could basically avoid this.
Right, yeah.
So if you find the editing tokens that seem to have this property, and then you somehow replace them with an index, or something that's their absolute, conceptual index, maybe that might help.
That's an interesting idea, definitely. I think something similar we tried is in the Moscow example. We just tried rewriting the sentence with Moscow, the capital of Russia. And what happened is that the side effect actually decreased. It was 0 out of 1,000 and it got back to 112 or 13. But the problem is the edit was not effective now. So it was like only able to recall the exact fact if we have the exact sentence. But if we ask anything about Moscow, it won't give the updated fact. So I think there's definitely a trade-off between specificity and the amount of side effect it has. But I think like your idea on finding some sort of index might be useful here. I'll definitely explore that.
Anybody else have a question for Himanshu?
This was great, by the way. I've not really immersed myself in this, and you did a really good job of showing all the various topics that are coming into play. The one thing I kind of want to talk about is, what do you think is the future of both evaluating model editing and kind of model editing in general, right? Because I think there's inherently two separate things that are going on. The first is that I think there's a kind of this space for a large model that's been trained on like a lot of synthetic data. And that then when you edit, you have a much more principled understanding of what editing means, right? Because say I want to remove like myself from a large language model, right? I can't just remove all instances of the word Arabic from the text, right? I have to remove me, I have to remove my associated MCDS, and et cetera, et cetera, et cetera. So I'm like wondering if you try to like change like the capital, like, move New York City to India, right? How do you handle all the other related facts to make that kind of reasonable? So and then the other thing is like, how do you kind of measure and understand these things?
Definitely. I think for the first part, this is something that I have still not been able to understand. Like, how do you substitute the holes that these factual edits create? For example, if we change Statue of Liberty is in Paris, what does this mean about the like the Liberty Island or something like the Hudson River? What entails? So I definitely think the future looks like where you don't have a single edit, but you have an exemplar set of facts that represent the concept that you're trying to change rather than a single sentence. And then for the second part, I feel that the ultimate evaluation techniques will be somehow informed by by a better understanding of the model internals. For example, causal tracing is just a simple way to understand where the fact is located. But maybe we just don't want to use that, and something that gives, rather than, like giving a location for a fact, it gives what are the set of hidden states that activate and in what sequence to manifest a given concept. And maybe those hidden states are worth looking at. So I think like it's going to be more centered towards model internals because the editing itself is informed by that.
Yeah, and the related thought I'm having is that if you move beyond word embeddings, sort of graph embeddings for words. Then essentially what you're going to know is not only sort of what are the other similar
Okay.
words that appear in the same position, but you're going to be relating that to all the other related concepts. And that's what he's getting. So
I see.
there's an example from my own life, which is I grew up in the town of Marblehead,
Okay.
Massachusetts. It has a lighthouse, but there's a Marblehead, Ohio, which also has a lighthouse.
I
Okay?
see. Okay.
So you have to be very careful with this, because if you say Nyberg visited the lighthouse in Marblehead, you could figure out that it's that one index, you know, of Marblehead, not the other. But if you just edit it by removing all of the token level information, you screw up all the facts that you have about Marblehead. So it relates to what we were saying before about indexing and tokens. You probably have to have some way of knowing, you know, what all those relations are. And the language models are not necessarily built to provide those, you know, kind of embeddings.
Right.
So you have to think about how you could actually model it.
Definitely. I think capturing the semantics, like when we're talking about an entity, what does it relate to? What is the context? I think that's important. And like, I think like that's the future way to go. Although in my work, I show word-to-vec embeddings. I did try GPT-2 embeddings as well, like getting the embeddings from the model itself, but that's very random. It does not render any useful effects. But this is, I think, open to research.
So it would be nice, this is, I'm asking you a lot, so
not an issue.
don't worry about this, but in the final report, it would be sort of interesting if you just speculated on how should we be training models and what characteristics should models have to basically avoid this, right? Because I'm not an expert in this, I'm kind of grasping at straws when we talk about graph embeddings. But I think eventually, where I think language models are going, is much more in the direction of hierarchical training and curriculum learning. So I would want to start out with a set of like universal statements that, let's say, will always be true, at least for the appreciable lives of the model. But then I may want to add other data, you know, to this. And then it would be fantastic if, when I'm now adding the information about Massachusetts, and then I'm going to add the information about Ohio, I realize, oh, wait a minute, is this the same Marblehead that I learned about before? Probably not. And I don't think there's anything in current language models to try to do this. That's a very simple thing for humans to do. They contextualize very well. And once we move to a more curriculum learning approach or a hierarchical data approach for training language models, it's really easy to see why the model should be able to do that. So if you could somehow reflect in your final report on the properties that models should have in the future, and why we would need to think much more about like partitioning the data, because essentially, if my model comes back to me and says, are you talking about Massachusetts or Ohio? I want to be able to say, forget about Ohio right now. And then, you know, in the context of this conversation, I want a local edit. Okay. But there's no handle right now. Suddenly you swap out all of that data. Right?
Definitely.
But if the thing came back and said, oh, you mean this, then I could literally say, yeah, let's only activate these parts of your training data. And then have conversation.
And what that kind of gets me thinking about is like the goal of language models, right? Inherently, there's like, and this is kind of that interface between like ICL and understanding what pre-generated software you're really trying to grapple with, which I, again, very respect. You want a model that is very good at reasoning, but like poor at remembering, or do you want a model that's better at remembering?
No, that's true.
That's a fair point.
Yeah, well, and maybe we need models, multiple models that emphasize different things, or, you know, there's a lot of work now on like chain of thought, chain of skills, where you have the same model that's designed to actually be able to do different kinds of, you know, responding. So that could be another way.
That's an interesting aspect. I'll include that in my report. But I think like this hierarchical approach, if we had access to like training models in that way, would really make editing simpler because we can define the scope exactly in the way we want it to.
Yeah, so I'm always thinking ahead to when we have embodied AI and we have different robots going around learning different things.
Right.
And eventually, when those two robots have a conversation, they're gonna have to introspect about why they have different thoughts and they carry different facts. And it's all gonna relate back to the experiences that they have. And when we get together as humans, that's one of the most interesting friendships that we can have is when we share those kind of complementary experiences and we learn from friends that way, right? But,
Right.
you know, right now, language models are kind of these black boxes. We're trying to probe them.
That is true.
All right, Himanshu, thank you very much.
Thanks a lot.